Now we're going to go ahead and learn how to evaluate a definite integral algebraically. So at this point, if I ask you to evaluate the definite integral of x from 0 to 2, we would go ahead and do it geometrically. So y equals x is my function, so that's y equals x, and I'm looking at this graph from 0 to 2. And since the graph is above the x-axis, I'm just going to look for the area. So this is a triangle, so the area of this triangle is 1/2, base is 2. This height is also 2 because this is the function y equals x. So the definite integral would be 2, which is the same as the area of the triangle. Now, the way that you can evaluate this algebraically is we can take the antiderivative. So the antiderivative of x is x squared over 2, and we're going to evaluate it at the bounds. So the way that you evaluate a definite integral is called your fundamental theorem of calculus. And what this says is you take the upper bound, plug it into your antiderivative. So you have 2 squared, which is 4 divided by 2, which is 2, minus, you're going to plug in the 0, which is going to be 0, and 2 minus 0 is 2, which is the exact same answer that you get here. Notice now here, when you have a definite integral, so you have bounds, you are not going to have a plus c in your answer because there's exactly one value for this area underneath the curve. I mean, if you really want to write a plus c, it would look like this, but what happens is those c's would drop out, so we don't write it. So make sure your answer is a numerical value. Okay, we could do the same thing on number 2. So if we do it geometrically, the function is 3. I'm looking at this graph from 0 to 4. So it would just be the area of that rectangle, which in this case is 12. If I do it using the fundamental theorem, we take your antiderivative, which is 3x. We're going to evaluate it. You plug in the upper bound, and you're going to subtract off what you get when you plug in the lower bound, which is 0, so which is also 12. Exact same answer. So there are going to be some problems that may be easier to do one method versus another, but we're going to practice a couple problems doing the fundamental theorem. So let's do these problems using the fundamental theorem. So these would be trickier to do using the graph. So I'm going to go ahead and find my antiderivative. So this would be 6x cubed over 3, which is really 2x cubed, minus 5x. I'm going to evaluate it on the bounds. You start with the upper bound. So you're going to plug in 3 for x. And then you're going to subtract off when I plug in negative 2 for x. And then you're just going to do this arithmetic, and if you punch this out, I believe this is 39. All of this becomes a negative 6, so this ends up being 45 as my final value for this definite integral. Okay, try one more. So antiderivative secant squared is tangent. I'm going to plug in the upper bound, so tangent of pi fourths is 1, minus tangent of 0 is 0, so this becomes 1. Okay. So let's talk about this last problem, this absolute value one. Now, I'm going to do it geometrically first. So this is a V-shaped graph. I know my vertex is going to be at 1/2. Looks something along those lines. And I know this is 1, because if I plug in 0 for x. So this is saying, look at the graph from 0 all the way to 2. So let's say 1's here and 2's here. So if we want to do it geometrically, you would just find the area of these two triangles and add them together. So the area of the little triangle would be 1/2, base is 1/2, height is 1. And then this triangle would be 1/2, base is 3/2, height ends up being 3. And you get 1/4 plus 9/4, which is 10/4, which is the same as 5/2. So this value is 5/2. Now, if you want to do this algebraically, what you would have to do is actually come up with the equation of the two lines separately and split this up into two separate definite integrals. So you would have to go from 0 to 1/2 and figure out the equation of this line, which is actually negative, or the opposite of 2x minus 1. So this is the opposite case of the absolute value. And then you would have to go from 1/2 to 2. And then this is the positive scenario of the absolute value. Do that. So the only way to do the absolute value pieces algebraically is to actually split it up into your two cases. And you can do the exact same thing. Take the antiderivative, plug in your bounds, and you would still get 5/2 when you do all the arithmetic. But this type of problem, I would say it is simpler to do it geometrically. So there are going to be some problems it may be easier to do geometrically than using the fundamental theorem.